Welcome to the solutions to the Regents Physics Circular Motion and Gravity problem set. Problems numbers 1, 2, and 3. Number 1. Imagine you are sitting in a car tossing a ball straight up into the air. If the car is moving at constant velocity, will the ball land in front of, behind, or in your hand? And B. If the car runs a curve at constant speed, where will the ball land? To help us answer A, let's take a look at this video. In this video, a guy is going to push this cart across the track, and you're going to see a ball pop out of this device right here. Let's see where it lands. Well, that's pretty cool. Let's take a look at that in slow motion. So the car is moving at constant velocity across the track. The ball is thrown straight up. What you have here is a neat application of your projectile motion concepts and this question that you're being asked going on at the same time. So because the car and the ball inside the car have the same horizontal velocity, the ball simply goes up as a projectile, its horizontal velocity remains constant, and it lands back inside the car after it's completed there. So the answer to A is that it would land in your hand. As long as we're neglecting air resistance, you're not tossing it up in a convertible or something like that. But if you toss the ball, the car is moving at constant velocity, you, and therefore the ball attached to you, are also moving at constant velocity. The ball will travel as a projectile and land right back in your hand. However, B, if the car rounds a curve, let's take a look at that scenario. Here we have a top view of a car that's going to round this curve, and we'll say that it rounds the curve in this direction like this. And so when we take a look at this, at the moment this car is at this spot shown right here, it has a velocity that is tangent to the circular path at this moment. So the car and you, the occupant, and the ball attached to you are both traveling forward. You let go of the ball, and it will stay in this straight line motion while the car and you attached to the car continue to travel in the curved path. This, of course, will cause the ball to land to your right as you continue to round the curve and the ball continues forward. The reason for this is that because the ball has its inertia, the moment it's let go is continuing in this straight line. So the ball's inertia is straight forward while you, attached to the car, continue to turn to the left. That's why the ball will appear, and does, land to the right of your hand. Okay, number 2. You swing one yo-yo around your head in a horizontal circle, then you swing another one with twice the mass, but you don't change the length of the string or the period of the revolution. All right, let's take a look at this, starting with a diagram. Here we have the yo-yo being swung in a horizontal circle about your head. What are the forces acting on the yo-yo? Well, we have its weight straight down, and we have its tension in the string pointed towards the center of the circular path. Well, what you've already learned is that because it's traveling in a circular path, this object is accelerating with a special acceleration called centripetal acceleration, which is pointed towards the center of the circular path. Well, if there's an acceleration pointed towards the circular path, there must be a force directed in that direction, or a net force directed in that direction, keeping it traveling in the circle. In this case, which of the forces is keeping the yo-yo traveling in a circular path? Well, you see, the only one directed towards the center of the circular path is the tension. So when we develop an equation for the first yo-yo, we would say sigma F equals ma. Is the yo-yo accelerating? The answer is yes, because it's traveling in a circular path. So we put the subscript C on our A. What force is causing the yo-yo to stay traveling in a circular path? And we've already answered that. The answer is the tension in the string. Equals m, and the formula, of course, for centripetal acceleration, v squared over r. There's our equation for the first yo-yo. What about the second one? Again, sigma F equals mac. Is the second yo-yo accelerating? Yes, it's traveling in a circular path, so we add the subscript C to our A. What force is keeping it traveling in a circular path? And the answer is, again, tension, but this time they double the mass of the yo-yo. So instead of m, now we have 2m, but they don't change the length of the string, so the radius remains constant, or the period of revolution, how much time it takes to get once around the circle. This would cause both of them, the length of the string, the radius remaining constant, and the period remaining constant, would cause the speed to remain constant. So what they're telling you indirectly in the question is that neither the v value or the r value will change. They're only doubling the mass. Well, what relationship exists between mass and tension in this particular case? Well, it's directly proportional. So if you double the mass without changing the radius or period of revolution, you double the tension. Next, number 3. A 615 kilogram racing car completes one lap in 14.3 seconds around a circular track with a radius of 50 meters. The car moves at constant speed. What is the acceleration of the car? Well, we start with the car would be centripetally accelerating because it's traveling in a circular path. And the equation for AC is v squared over r. The problem here is that while we know the radius, we know the r value, we do not know the v value. However, we are given enough information and we're told that it's moving at constant speed, and we know that v equals d over t. Well, the distance it would travel will be once around the circular track, so it would be the circumference of the circle, which is 2 pi r. The time is the amount of time it takes to complete one lap, and we call that period, the period of revolution. So you can see the d value becomes 2 pi r, and the little t becomes a capital T. The symbol we use for period in physics is capital T. Let's go ahead and substitute. And we have that v equals 2 pi 50 over 14.3 seconds, the period of revolution. This gives us a velocity of 21.97 meters per second. We now substitute that into our centripetal acceleration equation. So we have 21.97 meters per second squared, don't forget to square, divided by the radius, which is 50 meters. This gives us a centripetal acceleration of 9.65 meters per second squared to 3 digits. What force must the track exert on the tires to produce this acceleration? We start with our Newton's second law statement, sigma F equals ma. Is the car accelerating? The answer is yes, because it's traveling in a circular path. So we add our subscript c. What force is causing the car to stay in a circular path? Well, in this particular example, the force that's keeping it in a circular path is the static friction between the tires and the track. So we would say Fs is what causes MAC. Substituting the mass, 615 kilograms, and the acceleration we just calculated in part A, 9.65 meters per second squared, we multiply and we get a static friction of 5,940 newtons. That'll do it for our solutions to problems 1 through 3. More to come as we tackle problem number 4 in class tomorrow.